Raz, raz. Okay, I think that we can start now. Good morning, everybody. My name is Nabrzyski from PSNC. I have a pleasure to chair this session on grid monitoring and accounting. We have 3 speakers today, 30 minutes for each. I will leave like 5 minutes for discussion, and if there are more questions, then please, we try to maybe discuss it offline. Our first speaker is Joseph Legrand from CERN and Caltech. So Joseph is representing both CERN and Caltech from California Institute of Technology. And Joseph will give a presentation today on MonaLISA project. Let me first shortly introduce Joseph. So Joseph he was a member of the Monarch project, which was working on this hierarchical model for data grid systems. And as I understand, MonaLISA is just a follow-up project that is continuing to provide the tools for monitoring distributed environments. So please, stage is yours.
Thank you. I will try to describe this MonaLISA framework, which has been developed, started with a prototype in order to be able to understand distributed systems, to use this information in design and simulation, but as a final aim was to be able to develop this type of higher level services to optimize workflow in complex systems. MonaLISA is designed as a set of multi-threaded self-describing agents. And they are able to register and discover themselves in an automatic way. They can perform a lot of tasks like measuring, collecting data from other services, and in the same time to act on data, to provide alarm triggers, to take action if something is wrong. And in this way, in fact, we want to provide a generic framework in which we not only monitor what's happening, but we can also act dynamically on this information in order to be able to, as I said, to optimize the workflow in large distributed systems. I believe that an agent-based architecture provides the ability to invest the system with an increasing degrees of intelligence to distribute the work and in this way practically to reduce complexity and allow practically to manage global systems in real time. The main services or functionalities this MonaLISA service provides is distributed registration and discovery, which is based on the GENIE technology. Is a framework which practically allows to monitor or collect information from complex systems, describing computer nodes and clusters, network information, wide area network, local area network, is able to monitor application, jobs, or different other services, as well as a very important part in developing these complex systems is also to be able to monitor end-user systems, and in fact, these end-to-end performance measurements. So all these parts are designed as simple plugins which can very easily use existing tools. So our aim was not to reinvent the wheel, but to make a framework in which different tools can be easily integrated. It can interact with other services to provide real-time customized information. So anyone who wants to get information from MonaLISA can use this functionality to extract exactly what they want in the format they want. We provide a secure remote administration for services and application. As I said, this core part of agents, which is able to supervise applications, they can communicate between them in order to perform this type of optimized decision task in distributed systems. And also, we believe that a good graphical user interface always helps in understanding what's going on. So MonaLISA has 4 major layers of services. The bottom as this slide shows what is called this discovery network, or this GENIE lookup discovery system, which is practically the glue of the entire system. We currently run two networks, one which is a public one, which requires authentication, and it's a secure network. We have then this layer of MonaLISA services, which are in fact distributed services, able to collect information from different services. You can deploy agents in all these services. Then we have what is called a layer of proxies, which provide a dynamic load balancing between clients or other services which may want to have access to monitoring information, or in fact any other information. And this layer of proxies it helps to scale the system, so to have many clients where it's necessary. It also helps in providing a secure authentication for what different clients have access to see. And as I said, they are able to multiplex data wherever it's necessary. So this is a schematic view of what a MonaLISA service it is. Practically, this shows this lookup discovery, registration, and discovery mechanism we are using. We have a multi-threaded engine which is used for collecting different types of information. Different other services which can be used to store data, to have access via web services. The most important part is that anyone or any client or service can deploy dynamically here pieces of mobile code. And these are agents which can process data in the flow, prepare whatever the user or other services need, and send data back to services as they are processed locally in this framework. This is another view which also shows and emphasizes the security aspect of who gets access to what information in the system, as well as the fact that these proxy services are practically used as a gateway and multiplexer for the same information. So if we have multiple clients interested in the same data, they will be requested only once from the service, and then they are multiplexed to all the clients interested in this information. Yeah, it stopped somehow. I don't know, thinking to move to the next one. Okay, thanks. The same problem.
Try to jump to the page.
To which slide? Jump to this. Jump to this one. So we use MonaLISA in different communities, especially in high energy physics. It is used practically to monitor different grid systems, part of so-called high energy physics experiments, few of major networks in which we have agreement with them, like in Internet2, in Gloriad. We use it to measure the major connections between CERN in US, CERN into Ghent, and so on. And it has also been used in several major events for demonstration. This shows more or less some examples in how MonaLISA is used for monitoring Internet 2 traffic and all these Grid 3 funds which were set up in the US. So it's a relatively large-scale grid systems with more than 3,000 processing nodes in something like 30, 40 centers in the US. This is an example of using MonaLISA to monitor the topology of the wide area network and how we can perform something like trace route from each grid side to all the others and then combine the graph of connectivity for all of them. This is how we use MonaLISA to understand what's going on with jobs. So we provide a set of APIs which can be used to instrument jobs, and these are so-called lifelines for jobs or how a job is split in parts and how it evolves in time. As I said, we spent quite significant amount of time to include monitoring and network aspects into this monitoring framework. And this is an example of using a production network, Internet 2, for one of these land speed records tests, which has been done by some of my colleagues from Caltech and CERN. And this shows practically a traffic of more than 8.5 gigabits per second in a production line. We use MonaLISA also to control and monitor what is called this VRVS system. It's a video conferencing tool developed at Caltech. They have a large number of reflectors, around 70, all over the world. And practically, we use MonaLISA to monitor the system, to control its behavior, and in the same time, to optimize the communication into the entire system. So this is a slide which shows generically this APMON, which is used practically to instrument different types of applications. It's a simple library, APIs. We provide this API in 5 languages, so it can be used in programs, in scripts. And then they can practically send any information to MonaLISA, data, images, whatever you believe it's useful. You can also collect this information in a distributed way. You can control it from remote sites in order to send this information dynamically to wherever you believe it's necessary. So you can use a generic CGI or servlet scripts which take into account the destinations, the functionality you want to record and is sent to the right service. So practically this shows the fact that we can handle up to something like 5,000 such messages per second into a MonaLISA service and process it without losing any package. As I said earlier, it's very important to be able to understand what's going with end-user system, especially for interactive application. For this reason, we developed what is called LISA, a very simple agent, which can be dynamically deployed on any platform. It's based on a Java Web Start technology. This is used practically to understand the behavior of each end user, to be able to extract its hardware configuration, its drivers, operating system, to monitor whatever is important in the system, and also is able to send this information back to, let's say, one of these MonaLISA services we use to collect information. The main reason to develop this simple agent was to provide the functionality for end users to improve or efficiently integrate this type of large-scale application. So it's not only the fact that we monitor the end user, we use the discovery mechanism. And for an example, if we take the VRVS system, this is used to dynamically discover from which network you are coming, to connect you to the best reflector. If something goes wrong, to reconnect you dynamically to another service, which provides you the same functionality. So it can very well be used for physicists which are doing interactive analysis. They can dynamically find out which is the best place from the user perspective to access different types of data or information. As I said, an important part for us was to control this VRVS system. This is a simple example in which we have to provide for all the reflectors a dynamic connectivity and to keep what is called the minimum spanning tree, and to make this dynamic based on network conditions, and to, if something goes wrong with one reflector, to automatically reconnect all of them in such a way to always keep what is called the minimum spanning tree. This is an example in how we use this LISA and MonaLISA functionality to first optimize this entire video conferencing system by providing a minimum spanning tree connectivity dynamically adjusted for the reflectors, and in the same time to connect all the users to the best reflector from their perspective. Another example of using these higher level services we recently developed was to prototype using an optical control plane agent distributed system to practically provide an end-to-end functionality in moving data based on this type of on-demand optical path between different systems. So first of all, the system requires to create what is called a MonaLISA daemon, which takes into account the first one, the security, the credential for each user, and it is enough for this daemon to find one of the MonaLISA agents which are used for controlling optical switches. So our aim, in fact, was to create an end functionality for the user to copy data on a path which is dynamically created when you want to copy data, and to be able to achieve this practically in less than 1 second, independent of how many hops we have to create to create the path, and also the location of all these services. So the key in realizing this routing protocol, it's based on this distributed agent system. And as I said, they communicate between them using these proxy services. So practically our aim is to create dynamically an optical path from the end user. So this is an example on how we use the system to monitor the connections, the traffic in optical networks. So we set up mainly for learning and this prototype to test it. This setup, which is presented here, we have 2 optical switches, a Calian switch in Los Angeles and a glimmer glass switch at CERN. They are partitioned in such a way that each one looks like 3 sub-switches. And we have physical cross-connection between different ports in the switch to provide the configuration which I more or less show you here. And for the connection between LA and Geneva, we created 3 level 2 virtual LANs, which practically simulate the fact that we have three fibers in the system. This is practically used to control the switch through TL1 interface. I think it was important for us to show interoperability between the 2 types of switches. And also, very important is to have this end-user access to the system. I would like now, very shortly, to show you a little bit in how the system looks in reality. This is how the MonaLISA client looks. As I said, it discovers and connects to different services. You can see here the wide area network traffic we are monitoring. It has a function which... So this is practically the links we have in Internet 2 in US. As you can see, the real traffic on these links goes now to something like 1.5 gigabits per second. This is a transatlantic line between CERN and Geneva. We monitor. We perform simple, what is called ping test measurements between the sides. We have this type of grid services. Where you see red lines, usually it means that there are firewalls, which is a big problem in developing any kind of new grid systems, we can, in fact, if I go to this, let's say, sun side, this is one of the biggest so-called farm we have. It's more or less all the public services at CERN. So this MonaLISA service, for example, is monitoring more than 2,000 computers, and it collects about 55,000 parameters. So the biggest cluster we have is this LX batch with more than 1,000 nodes, 102,000 nodes. So for example, if I want to see the CPU per user to all these nodes, it does this request to CERN to send data. It should send us an answer quite soon, so you have a real-time histogram of all the nodes and the load in the system. It can also be used to show other types of parameters. For example, if we go to the mass storage system at CERN, which is the cluster grid, we can take, for example, the traffic which is done. We can create this type of histograms in how much traffic goes per each major server in the mass storage system. We, for example, monitor here at CERN the traffic in major networks. For example, this is the traffic from CERN into GÉANT. We can get the history of this for the last 2 hours, the last 2 weeks, or whatever you want, and you can see the traffic which goes into GÉANT from CERN. Or it can, the same, we can see the production into the US network, which is a direct link from CERN to Starlight. As I said, this part can also be used to show the traffic in wide area networks. This is a different view, the traffic on all the major networks. These are real-time information. Then every new measurement is reported back to each client which starts this application. We can also see the load on all the grid sites we are monitoring now. So you can see the number of nodes which are used, the number of nodes which are free. All this is, I don't know, the ways resources are used in all these grid sites. As I said, for applications, it's important also to be able to see the number of jobs and the number of jobs which are queued, the number of jobs which are in execution state. And this is shown in this graph, so you can also compare with number of CPUs with other type of jobs which are executed in the system. So you can easily compare what types of jobs are running in the system. As I said, for us it was important also to be able to monitor the topology of the network. So this shows, let's say, the IS connectivity between the major sites we are using now. This allows practically to find out also which is the best way to go from one side to the other one. In blue, it shows the real path. In orange, if it's another or a better possibility to connect two sides, you can. Also shows this in terms of routers. It's a little bit more complicated now. But for example, if I want to see not all the routers we go through in this grid system, but for example, if I take only the GÉANT routers, it gives me which are the routers involved, the way they pair with other networks, and so on. This is another example of using the same functionality to find out, for example, which is the best way to replicate data from, let's say, one one regional center to all the others. So this is practically a way to create a minimum replication path between, let's say, one side and others in the system. So usually it's able to create this dynamic tree for best replication of data among grid sites. I would like now to also show you the part which we have for optical switches, and the example I told you earlier. So here we have this system I described you earlier. So I will just try to show you, for example, I have some simple windows here. So if I start something like MonaLISA iPerf measurement to GVX5, for example. I am on GV2. This creates dynamically a path, and it shows you how data are transferred into the network. So to create the path practically was necessary to use this in 400 milliseconds. The measurement was done is 800 megabits per second. They are connected with optical fibers at 1 gigabit port. And when the measurement was finished, the link has released and everything. So this is another example of trying to transfer a file, for example, to LAX3. I have a few test files here. So this practically will start the transfer if the link has been released. Let's try to, sorry, I made a mistake here. So this practically, it's transferring now a file from this computer to this one. When the transfer is finished, it will release a link, and it can be used by other users. We can also, you can see we are using scopy to copy the file. For example, I can start this transfer again, and maybe another one from here. So as you can see, it's another transfer which is started in this framework. So in principle, we create this path in a dynamic way. They can be reconnected if something goes wrong. Agents are able to reconnect the switch or use an alternative path during the same transfer if something is going wrong, and reconnect them into the system. The same framework is used now to control and monitor the glimmer glass switch here at the glimmer glass stand. So for example, if I start now the discovery for the glimmer glass switch, I will saw and be able to control exactly what these switches are doing here to send video signals between DVD players and images. So the configuration used by them is now discovered, and I can go, for example, to control through the admin interface I told you earlier, every switch. So I can see the ports in every switch and be able to reconnect them, to stop connection, and so on. So for those which are interested in more details in how this part works. We have a small stand here, and I would like to invite you to show you more about this part. So just one more slide here. I think our aim is to also extend this quite soon, perhaps, to be able to work with GMPLS systems where they are available in networks. But I think it's also important to be able to control directly optical switches, especially in major labs and where we have powerful systems. So MonaLISA is a framework which should be used to integrate and help to integrate these major parts we have in our system related with information about networking, farms, and data servers and application. So this should be used to correlate information between all these major three parts and use them for global optimization in the system. This real-time feedback between major layers is really important to be able to create this kind of load balancing and self-organizing in large distributed systems. So I think I more or less managed to show you more or less the features we implemented in MonaLISA. I want to tell you that it proved to be a stable and reliable service. We run more than 200 such services in the world. And more information you can find at this HTTP address. Thank you very much.
We have time just for one question, short question. Anyone? Brian? No. Okay. Okay. No questions. Thank you very much again. Our next speaker is Sergio Andreozzi from INFN, Italy. And Sergio will present to us his work on GridIce system, which is the monitoring service for grids. Sergio was working in a data grid project, and now he's working for the EGEE or EGEE. There are different pronunciations of this project. So yeah,
data tag.
What do you say?
I was working.
Oh, also data tag, right? Data tag. Okay.
Good morning, and as Jarek introduced me, I am Sergio Andreozzi for the National Italian Institute of Nuclear Physics, and my talk is about monitoring grid systems. I will present you in particular the details of the GridIce architecture, that is a tool that we have developed in the former European data tag project. And currently, this is being evolved in the context of the EGEE project. In order to let you better understand the issues related to the monitoring of a grid system, I will first set out what are the basic principles behind a grid and what are the basic concepts that typically are part of a monitoring service for distributed systems. After that, I will list a set of use cases that driven the development of GridIce. And finally, I will give you the details of the architectures, and you should be able to understand why we have made some choices. So let's start with an example. Let's make the hypothesis that we have two sites. With each site has resources that can be computing resources, storage, or databases. And each site, in order to access the resources, you need login local credentials that typically are login and password, for example. And these two sites may have different technologies also, so you may need to use different clients in order to access the resources. Let's make the hypothesis that a subset of users of site A and site B want to collaborate and share part of the resources, part of the site. Without a grid, each user of one site should have a local credential to the resources of the other site. By using a grid system, we can virtualize both resources and users so that we decouple from the physical details, and we are able, for example, to create local identity. We are able to create pools of virtual resources that are mixed and that are composed by resources of the different sites. And we have also grid identities that typically are for users, that are typically certificate X509. So the first basic concept of grids is the virtualization. Then we need a functionality that is able to map the resources from the virtual pools to the physical ones. The other core functionality is the ability to map virtual users, that are grid users, to local credentials. Once we have these three main functionalities, we can set up sharing of resources across different administrative domains, and we are able to provide users with the capability of accessing the resources in a transparent way. So here we have a more rigorous definition of a grid system. Extending our example, others main concepts are that the resources are distributed worldwide and that they are, as we have said, they are heterogeneous. And the important is that these virtual pools of resources can dynamically change over time. Now let's move to the concept of a monitoring grid system. Monitoring is typically the activity of observing a system in order to understand if something is happening. In particular, some events that we are interested in. About grids, we are interested, for example, in understanding what is the current composition of resources, who is currently using these resources, and if the grid performing as expected, for example, or we want to detect in advance possible false situations. So we said that the important activity of monitoring is observing. That means measuring parameters. How we perform this measurement is really important, because if we don't, because the measurement is associated number symbols to features that we are interested in. The process by which we make this association is really important, because if we don't do a clear measurement process, the data that we get from the monitoring cannot be used for performing meaningful analysis. Then we have the concept of event. This concept has been defined in the context of the Global Grid Forum. An event is basically the result of a measurement to which we attach the timestamp representing the instant of the time when we run this measurement. And then we have the event schema, that is the set of characteristics of a system that we are interested in. Monitoring distributed systems is based on four main phases. The first one is the generation of the events. The generation of events is done by using sensors that runs on the target machines. And these sensors can be categorized, for example, as active or passive, depending if they trigger some activity on the target entity being measured, Or, for example, they can be categorized intrusive and non-intrusive. We can say that a sensor is intrusive if the measurement process can affect in a noticeable way the activity of the target entity that is being measured. And it's important to pay attention to the design of sensors that are intrusive. Once these measurements are done, we need to distribute the data, the monitoring data, to the interested parties. In order to decide which distribution process we want to use, we need to make choices. For example, what is the distribution model? We want to choose pull or over push, aperiodic versus periodic, or unicast versus multicast. And also we can have, for example, hierarchical distribution process. Once the monitoring events are distributed, we need to present to the final user. In order to present meaningfully all the monitoring events, we need also to abstract and aggregate them, for example, because the set of measurements is really, the set of monitoring data is really huge. We need to somewhat give to the user only the meaningful information that let the user draw some meaningful conclusions on the behavior of the system. This is important because if you have an excess of information, the user is not able to draw any conclusion, any meaningful conclusion. Along all these three steps, we have a processing phase that can apply to each of these, and where basically we aggregate. For example, we can filter the events if they are not relevant compared to the previous measurements. We can aggregate them or compute the aggregate metrics. So these are the main concepts about monitoring. Now I want to give you some use cases that we have collected from users of a grid system. Typically, we have different roles in a grid. We have, for example, virtual organization managers that are the person that are responsible for the resources that are assigned to a virtual community of users. And these are, for example, these persons are interested in understanding what is the current composition of the resources that each user of virtual organization can access. He can be interested in understanding how the mapping functionality from the virtual resources to the physical one works. For example, if there are unused resources, why these are not used? Maybe because the requirements of users that are using the grids do not map any of the resources, or maybe because the mapping functionality from virtual resources to the physical one is not working properly. And then, for example, another characteristic of a grid is that you cannot repeat a job execution in the same way you did, in the sense that each time you run a job, your job can end up to a different resource because you don't control that. Therefore, it is meaningful to be able to record some interested metrics so that the virtual organization is able to run some analysis on the past execution of jobs in order to understand how their application is performing. Other users of a grid system are, for example, system administrators, that are the persons that are managing resources that are being offered to a grid system. And, for example, they want to visualize among the managed resources how the ones that are interfaced to a grid systems are behaving. Or, for example, another user of a grid is, the end user, this is the one that is actually using the grid. And, for example, he wants to know if his job is working. That means once he submits a job, he knows in which machine he finishes. But he doesn't know what he's doing in a certain moment. He would like to know if, for example, he's consuming CPU, because if there was, for example, some error in the configuration of the input data, and this job is hanging, waiting for data, he doesn't want, and if the job takes a long time to reach the end, it doesn't want to wait hours in order to understand that there was a submission problem or a configuration problem. Another important set of users of a grid are the persons that belong to a grid operation center. That is the organization that is taking care of coordinating all the grid sites. That means, for example, if you have to run updates, all the grid middleware, or running some high-level management activity, and they want to have a clear composition of a grid divided by site, for example. They want to receive notification if there is some fault situation. So now we move to the details of GridIce. The first step that I presented about the monitoring was the generation of events. In GridIce, the process of measurement are typically Perl or C programs. The event schema is based on the glue schema. The glue schema is a description of grid resources that is currently used, for example, for workload management. That means for describing the characteristics of resources in order to give final users a kind of a dictionary that this can use in order to express requirements on the desired resources. We have made some extension to the glue schema in order to capture also the monitoring use cases, because this was mainly designed for matchmaking. For example, we have added network-related attributes. We have added information about the usage of jobs. And also we have more detailed system-related attributes. All the sensors are executed periodically, and thus they produce the desired metrics. Once these have been produced, we need to distribute them. We have said that grids is across administrative domains. The first problem is that each site has its own local monitoring service, and a grid monitoring service should be able to integrate with the local one in order to avoid to have proliferation, for example, of monitoring services. So, for example, we have in GridIce we decided to rely on fabric monitoring service in order to collect and to run the sensors, to collect them at a single point, and then to expose them to the grid. So we have a hierarchical model of distribution. There is a first level of aggregation of monitoring at the site level, and then there is a second level exposing this information to the grid. In order to decide which is the interface and the service to which this monitoring data is offered to a grid, we have chosen to interface them to the grid information service. That is a service, a key component of a grid system that already is offering some information on the status of machines. We have decided to use this service in order to have a common interface to the monitoring data. Once this monitoring data is offered to the grid, we have a component that is the GridIce server that can focus on a certain scope of resources, can collect them, and then offer the aggregate information to final users. Concerning the data delivery model, we have a default, for the fabric monitoring, we offer a default solution that is, we use Lemon, a tool from CERN, and this uses a push delivery model. The data are then offered to the grid by a pull model, and then the final consumer, depending on the client application he uses to access this data, can have both push or pull. For example, pull if using a browser or an application to access the monitoring data in XML format, or push if he wants to subscribe for some events about about some aspect he's interested in. This is an example of how currently we deploy GridIce on the LHC computing grid. We have 2 sites in this context, and we see on the clouds are basically the Lemon agents that run the sensor of the machine, send the data to a collector machine within the site, and that this monitoring data are exposed using the grid information service of the current LCG production system, that is the Globus MDS version 2. Then you can set up a GridIce server to monitor a certain set of resources. So this will run discovery phase of the resources that you want to monitor, and they will periodically collect the information and present to the final user. So going more in details on the structure of the data generation and distribution, on the left side you can see the main roles involved in the GridIce. In the bottom part we have the resource, that is the target entity being monitored. Then we have the site publisher, that is the component that collects the data within a site and expose them to the grid. Then we have the GridIce server that makes aggregation of this data and offers the information to the final user. So sensors run on the resource, then these events are collected in the site, and the choices for LCG are for the collection within a site we offer the default choice of Lemon. Then these data are offered by using the grid information service, and once they are collected in the server, they are offered through different means. Here we have a summary of the data delivery model that apply to each level distribution. What we are currently doing now, we are designing the evolution of this system within the context of EGEE. The middleware developed within EGEE is called GLite. What we need to do in order to move this system that is currently in production to GLite is basically we can keep the fabric monitoring part. We need what is happening in GLite is that the grid information service is changing. There is not MDS, there is RGMA, but there are also other solutions to publish the monitoring information. For example, there is a component called CMON. So therefore, we are moving from de facto standard, the grid information service, to a set of publishers that can offer monitoring data using grid interfaces. So the server needs to be updated also in order to be able to collect information from different sources. This is a basic synthetic structure of the server. We have the bottom layer where you have the discovery component that basically can be set up in order to, for example, if I'm the VO manager of the VO Atlas and I want to set up a server in order to monitor the resources that apply to my users, I will set up it in order to discover all the resources that dynamically appear in the grid that can be accessed by users of Atlas to be monitored by the system. The discovery components runs this activity, that is periodically discovering what are the resources belonging to Atlas that can be accessed by Atlas users. Once they are discovered, there is a scheduler that is programmed in order to periodically run consumers that go to the resources, to the site publishers of monitoring data and collect them. These are maintained in a persistent storage. And then there is an abstraction layer that translates the data in XML so that they can be offered through different means. For example, to browser application using HTML, to applications that want to access monitoring data using XML format. We have also a notification service that can be used in order to have timely notification, and this is publish subscribe based. That means you can set up, for example, an XPath expression of some metric and receive a notification when this XPath, when the predicates related to the XPath apply to the match some event, some monitoring data. We have also a component that generates the data as graphs. What we need to do in order to evolve also this system for GLite, we need to change these two basic components. That is the discovery, since the grid information service is changing, and the consumers that need to be able to access data from different interfaces. This is a first screenshot of GridIce. For example, this is providing data aggregated by administrative site. Each line refers to a site offering grid monitoring grid resources. And we can have, for example, we see the country to which this site belongs. We can see some information about computing resources. For example, how many entry points for computing resources you have. That is the GK column, the fourth one. And then we can see how many batch queues are available, how many running waiting jobs are present at the moment on the machine. And then we have also information about the storage resources. This is another view about the status of services. Always this is, for example, a view interested for a grid operation center, where for each site you see how many grid services are being running and if some of them has some problem. For example, here the main grid services that are considered are the resource broker, the BDII, that is the root of the information service. Then we have computing elements that are gateways to computing resources. We have storage elements that are gateway to storage. And then GC is the GridIce collectors. And then the last part on the right, we have other services that do not apply to these categories. Now we have another screenshot about the detail of jobs. For example, here we can see all the running and waiting jobs for the VO Atlas. For each job, we can see the details. For example, we can see the site in which is running, the status of the job here. And then we can see when it was created, the starting time. That is the difference basically from the creation, so for how long it has been running. Then we have the final duration that will appear at the end of the job. And then this is, for example, an attribute was asked the rate between the CPU and the wall time. So you can have an idea if your job is consuming CPU regarding the time it was on the machine. And then we have the RAM, memory, and virtual memory used. And also, if this was submitted by a resource broker, you can see which is the resource broker from which it was submitted. We can also have some graphs about the evolution over time of running QA jobs. Then there are also other graphs available. The current status of the GridIce is that is integrated and deployed with the LCG computing grid, and many GridIce server installations exist, each of them with different scope of grid resources. For example, we have one GridIce server monitoring the Italian resources, one monitoring the GILDA resources, then for the LCG wide or for subset of these resources. Also, there are VO-based GridIce server installations. In the short term, what we plan to do is to harmonize the sensors. For example, in the next talk, you will see how that there is an overlapping of the metering service from the monitoring point of view and the accounting point of view. And we are trying to have a common sensors in order to avoid to first duplicate work, second to avoid to overload the systems, because for example, sensors related to the job are to measuring attributes related to job can be heavy on the machines where they run. Because, for example, if you have a batch system that is managing thousands of jobs, and you want to get real-time information, that the load on the machine can be high. So it is important to avoid duplication. Then another problem is that there are sites that don't let you install sensors, they don't let you access log files, so you cannot go there and say, please install this software that is going to your log files, for example, your batch system, and extracting information. This is because, for example, they may be offering the resources to other users that are, for example, to other companies or that not related to grid, and they don't want anyone be able to access the information of these systems. What we need to do then is we need anyway the information about the usage of jobs, the usage of your farms on the grid point of view will give you a way to provide us this data. And then another important requirement that is being required is about enable a fine-grained security on the access of monitoring data. That means, for example, if I am the VO manager of a CMS, I shouldn't be able to access the details of jobs of another VO. Then, we need to deal with different producer interfaces for monitoring data, and then provide end users with a more fine, flexible way to understand what this job is doing on the machines. In conclusion, we have seen that the monitoring of a grid system is a complex activity. The actors that are interested in monitoring data are different. They have different requirements. We have designed the GridIce of trying to follow all these requirements. There is lots of work to do. Anyway, the current experience in production environment is positive, and in the short term we plan to work on harmonizing sensors, supporting better security, and dealing with multiple producers. In the middle term, we can plan also to evolve the distribution model to, for example, new appealing technologies like peer-to-peer systems or publish-subscribe systems. Here we have you have a set of references where you can get more details about either GridIce or documents that I used to prepare also this presentation. Thank you.
Thank you very much. We have time for questions. Yes, go ahead. Just a moment. I'll give you the mic.
Hi, I just wanted to know how much network-related information you have introduced, and what are your plans to grow them, and what kind of information you're keeping?
Yeah, thanks. You have a paper about this. This is number 5. That our problem was how do we measure the network-related information. I mean, the monitoring of network is well known. There are lots of parameters, lots of well-defined parameters and tools to measure them. From the grid point of view, the problem is how, since you have a worldwide system, distributed system, how do you measure this information and how do you aggregate them in order to be able to use, for example, to run scheduling, selection of resources. And therefore, we have defined a kind of model that let us able to basically how to deploy the sensor for networks in order to be able to be meaningfully used for resource selection. In particular, we have a concept of domain. We define a domain as a set of grid services that share the same connectivity. What we do is we measure network-related parameters only between domains. And then we maintain the ownership of a service to a certain domain so that we are able to make some selection choices. At the moment, we are deploying this system in Italy, and the parameters that we monitor are, for example, the packet loss, TCP. I don't remember if the TCP band achievable bandwidth should be on demand because it's an intrusive measurement. And then we have the clock skew, and we have a kind of 10 different parameters that we can round trip, one-way delay, the classical network parameter. Let's say that the important message is that for a grid system, the issue is how do you aggregate them, since you cannot, you cannot think to measure all the information end-to-end for each service because it does not scale. The idea was to find a way to aggregate them in order to be able to meaningfully use this information.
One more question? Okay, go ahead.
How much do you have to change this GridIce if you want to run it on another grid infrastructure? Or in other words, how much is it tied to EGEE?
Okay, depends first on the grid information service being used in this system, in other grid infrastructures. If they use MDS, okay, it's not so difficult. If they use a different grid information service, basically you need to rewrite how you interface local monitoring data to a grid information service, and on the server side, how you query the producer of information data, and you translate in a local format so that it can be elaborated by the server. Then it depends on there might be some dependency on the job-related information, because typically we rely on information in order to, for example, understand the grid identity of a user that submits a job. We rely on Globus-related log files, for example. So there is some, the more important part, let's say, are some part on sensors that relates to the grid information, how this grid information can be extracted from the local system, and then how you interface this data to the grid information service, and how you translate then from the grid information service to the local format of the server. So there are different...
Okay. Okay, thank you very much. Thank you again. I don't think we have time for more questions. Thank you very much. And our next speaker is Andrea Guarise from NFN, Italy. And Andrea will talk about the accounting system in the EGEE project, about the common practices actually for accounting in this project.
Thank you. Do you hear me? Oh, no, don't worry. Okay, I'm Andrea Guarise from INFN, Italy, and I'm currently working for the EGEE project, and I'm responsible for developing the accounting system of the GLite software, which is the software developed within that project. So I will start with a generic introduction about the terminology currently used when we speak about accounting, and after this first terminology introduction, I will talk to you about the DIGAS software. So the first step, and probably the most important one when we are talking about monitoring and accounting, this is rather a common piece for those two aspects, is the metering phase. Metering is essentially the phase in which you measure the user payload that is currently happening on a resource. That is, when a user submits an execution request, a job, to the grid, it gets executed somewhere. For example, in GridIce, it is usually a batch system. You need to measure the resource usage for the user job and report it to the accounting system. For example, it is important and commonly understood that you need to measure things like the CPU time consumed by the job, or things like memory or disk occupancy. But when you are talking about grid accounting, you need also to be sure to have information such as the unique identifier for the user, that is, for example, the X509 subject of the certificate that is being used as a credential, or a grid unique identifier for the job, since you don't care much about local job IDs. Those informations are usually addressed as and called usage records for a job. Once the metering step is concluded, you simply need to send those information and archive them on databases. There are some requirements about accounting databases that information stored within needs to be confidential. That is, only authorized person need to have access to those information, and the reason is very clear. Then there are some security aspects, that is, information traveling to the accounting server needs to be encrypted and signed, and this is done by using the appropriate credential, usually the user's one. Then, since we are talking about a grid service, it's essential that the architecture of the system be distributed, reliable, and communication mechanism need to be fault tolerant. That is, if some of the services are unavailable or there are network faults, you need to be sure not to lose any usage record. This is essential when you are talking about accounting. After these steps, there is the usage analysis of the user jobs and of the transactions that are occurring. That is, the information archived in accounting database are very complex. There are many records, many types of information, and not all the users of the accounting service are interested in all the information archived. For example, there are different types of users, a common user, the one who submits a job, simply needs to know how he used the grid for his job. So he doesn't care about more things. But, for example, a site manager needs to know who used his resource, how, and eventually track a single job. Don't care about which user, because, for example, it caused some problem to its system. Then a virtual organization manager may want to know, and probably will, how the user under that VO are using the grid. Then the most interesting for some partner part of accounting and grid accounting is the pricing of resources and charging and billing of users for their usage. I know that mainly in app physics community, people doesn't want to pay for what they do, but in other community, when grid will become a commercial reality, there will be the need to charge the user for their resource usage. So there are some steps in pricing and billing, and essentially you need to establish a price for a computational resource. Then you already have the metrics measured during the metering phase, and according to the price assigned to a resource and to the metrics, you can compute a cost that is assigned to the particular job executed on the grid, and finally, eventually, you can charge the user for its resource usage on the grid. Okay, now I can talk to you about the GAS, that is the way in which GLite implements the theoretical concept I just introduced you. It is conceived as an economic accounting system, that is, it wants to allow grid managers to charge users for their usage. It is implemented as different layers that independently solves to the steps that in their aggregate form the accounting. Since the GAS is developed within the context of the workload management system of the GLite software, it may be important to show you how, in principle, a job submission works. That is, the user submits usually a job to a user interface, and the user interface now with common APIs submit a job description to the workload manager that is part of the GLite software. At this point, the workload manager can eventually contact a price authority, that is the authority that assigns prices to resources, to get back a list of prices for available resources. Also, according to these parameters and other parameters about resources, a computational resource is chosen for the user job, and the job is physically submitted to the computing element that will execute that job. The job runs on a batch system, and the usage records are collected and then sent to the accounting servers. I will come back to the details later on. The first step is metering. The metering is done by sensors on the computing elements, and they simply aggregate the batch system accounting information to the grid related information for that job, that are the grid job ID, the computing element grid ID, and the user grid identity, and some other details needed to unambiguously assign a job to a user. This is a representation of the architecture of the Janduia software, which is the metering system adopted by the GLite software. It is not really important to understand the details. The most important thing to know is that this sensor system aggregate the batch system accounting logs with grid-related information and stores all the information for each job in a repository that can be used by the DGAS service, but also by other services that need to have access to job usage records in a grid-friendly way. For example, there is actually an ongoing activity to integrate the GridIce monitoring system with Janduia software in order to have a common base for the metering infrastructure. The accounting phase is rather simple. The usage records, once collected, are sent via appropriate APIs to the accounting servers that are distributed by nature and stored in relational databases for further analysis. Now I can try to show you better how things work. For example, here we are a deployment schema of the DGAS software. The DGAS accounting server are known as HLR, Home Location Register, and as you can see, in this example, we have 3 virtual organizations with their users. In each virtual organization, there is an home location register server where the usage record for the user job will be archived. Then we have 3 sites that have their own computing element, their own grid resources. 2 of these sites, Site 1 and Site 2, share a common home location register where the computing elements are registered, and then a third site, Site 3, has its own home location register. What does happen is that when a user submits, for example, 2 jobs to the grid and they land on 2 different computing elements belonging to 2 different sites, for example, a computing element in Site 2 and a computing element in Site 3, the job gets executed, and once collected, the usage records are sent to the user first, to the user's home location register, where are both archived. As you can see, usage record 1 and usage record 2 are then available to the user home location register that is in HLR2. At this point, with a double commit so information can't be lost, a copy of the usage record is also archived on the corresponding home location register for the computing elements. So the usage record 1 corresponding to the job 1 that's executed on computing elements in Site 2 is archived in the HLR for Site 2, and the other usage record for job 2, usage record 2, is archived in the other home location register, that is the one for site 3. This way, it is possible for the user to have access via a query to his own home location register to both the usage records of his jobs, so to all his job information, while to site manager, for example, of site 2, with a query to his home location register, which in this case is home location register 4, he can have access to the usage record of the job that currently run on his resources, but he doesn't need to have access to information that belongs to the other site, site 3. So information are widely distributed and are available to people that are interested into. Then, since there is also the need to have access to a wider aggregation, for example, the overall grid aggregation for some of this information, it is being studied a process to aggregate information via Apple, that is another part of the GridIce software that will present aggregate information, for example, for all the grid, without losing confidentiality, because only anonymous information will be presented at this level. So, the next step in accounting is account balancing and resource pricing. That is, as I said, you need to assign a price to computational resources. In the GAS, this is achieved via a network of servers that are called price authorities that assign and stores the price assigned to the resources. There can be an arbitrary number of independent price authorities, and we suggested to have at least one price authority per virtual organization or per site. It is prices can be assigned manually by site manager, or it can be possible to have automatic algorithm that, for example, basing on computing elements load, workload, can assign a price in order to help the workload management system to balance the load on the grid. When you have the price and you have the usage records for a job, you can then, with a definable algorithm, compute a job cost and subsequently charge the user account and hence credit the resource account for the job that has been executed. Billing and charging. As I said, it is possible to bill a user, to actually charge a user for his resource usage and have an economic transaction between the user account and the resource account, but it's not mandatory in the architecture. It's an optional feature, since not all of our customers will be interested in this phase. So the implementation of this process is rather general, since we don't want to put rules on how the charging phase is done. Rather, we want to let resource owners decide whether and how they want to charge their user. We simply give them the possibility to do this. Then, at the end, I can show you how economic accounting can be used in this context. And we have a user with an account. The green bar is his fund availability. He submits a job to the workload management system. At this step, there is his economic authorization, is fund adequacy is checked, and if he has enough grid credits to submit a job, the job is, as usual, submitted to a computing element where the job runs, usage records are measured, usage records are sent to the user, in this case, home location register. The price valid at that moment for the computing element is requested to a price authority. Then there is an exchange of usage record between the user HLR and the resource HLR. It's not shown here, but the cost is computed. There's a double commit phase and the debit credit transaction process, and funds are transferred to the computing element account. Then, an hypothetical scenario, let's suppose that this organization where the computing element has also some users, the fund can be, for example, redistributed between the users of that organization. For further information about the DGAS software, we have this web page, and thank you for your attention and for your patience. If you have any question.
Thank you very much. Yes, we are a bit late, but we still have time for questions, if you don't mind, of course. Any questions? Okay, I have one question maybe. So is there any business model behind GLite? So you have any business usage of it?
No.
Or plans?
There are, as far as I know, since I'm only a developer, there are not yet business plans for GLite, but we suppose that if the GLite software will be widely spread, there will be customer that will be interested in using grids as a commercial, from a commercial point of view. So an economic accounting is important.
I understand. So I have also maybe more general questions about GLite. So GLite is actually the, let's say, core grid middleware layer, right? So it's like a competitor to Globus or Unicore. I know that there is a very first version of GLite available right now, and it's under stress testing and stuff like this. But could you compare it to GT4 somehow? I mean, how does it relate? What are the comparisons, performance analysis, etc.? Do you have any comparisons so far?
I can't answer this.
Okay, maybe it's the question.
This question, I'm not the right person.
Yeah. Okay. Another question? No. Thank you very much, Andrea, and also to all the speakers for this very, very interesting session. I hope you enjoyed it, and have a nice time during your lunch now. Thank you very much.